Hi everybody, I wanted to work a problem from work session 17, question 7. The problem states a 0.446 gram sample of an unknown monoprotic acid is titrated with 0.105 molar potassium hydroxide. The resulting titration curve is shown below. Determine the molar mass and pKa of the acid. All right, so as we see here in this problem, we have a titration curve. We have to get some information from the curve before we calculate molar mass. And what we'll notice here that we start with the acid, that's what's in our beaker, and it's monoprotic. So that means when we reach the equivalence point, the moles of the monoprotic acid will equal the moles of the potassium hydroxide that's in my burette. And I'll draw that in a little bit. So that's when you always hear the moles of acid equal the moles of base. So we will be able to find the equivalence point, and we'll have to approximate it. So if you did this problem and you get slightly different numbers than I do, that's okay, because it's an approximation with this problem by reading this graph. But usually the equivalence point is halfway up the steepest part of the curve, and so that would be around here. And I would estimate the equivalence point to be, and so therefore I would like to see how much of that base was added, the volume of the potassium hydroxide. I estimated it to be about 35 milliliters. And so we're going to use that number. Just wanted to show you on the graph where I got that from. So once again, the equivalence point is halfway up that curve. And then if you come down here, you can see that it was approximately about 35 milliliters of potassium hydroxide was added from the burette during the titration to reach the equivalence point. Now, half the equivalence point is when you add half that volume. So you have 35 milliliters, then you're thinking maybe something about 17 milliliters that's added. And so the pH is equal to the pKa at half the equivalence point. So I would estimate the pKa of this acid to be about 4.1. I think if you're taking my class, in my class answer key, I had said about 4.5. There's definitely some variation here since the graph is a little small, but you would get that from half the equivalence point. Right? Okay, so let's write that down. Where do we get that at? So pH is equal to pKa at 1/2 the equivalence point. That actually comes from the Henderson-Hasselbalch equation. pH is equal to pKa plus the log of the conjugate base of the weak acid over the weak acid. So when you are at the half equivalence point, then the concentration of the conjugate base is equal to the concentration of the acid. Basically, that acid that's in your beaker, remember, always draw it out. So what's initially in our beaker is this acid, and what is in our burette is that strong base. We're doing a weak acid strong base titration, so KOH. When I've added half the volume of the KOH, that means that I've depleted the moles of the HA, or the concentration of my weak acid, by half its amount, and in doing so have created its conjugate base. And so at half the equivalence point, the concentration of the conjugate base of my weak acid is equal to the weak acid itself. And if you were to plug that into the Henderson-Hasselbalch equation, you would get 1, right? Because these would cancel each other out essentially. And log of 1 is 0. So therefore, pH is equal to pKa at half the equivalence point. All right, so that's a good one to remember. And like I said, you can always derive it from the Henderson-Hasselbalch equation, like I've shown you now and I discussed in my online lectures. All right, so therefore, the answer to the pKa of this unknown monoprotic acid, is anywhere, if you wrote 4 to about 4.5, that's totally fine, since you're estimating it from the graph. All right, also from the graph, we want to figure out the molar mass. So molar mass of the acid, remember, is the grams of the acid over the moles of the acid. Now the problem, when we read it, says that we put in 0.446 grams of the monoprotic acid. So that's how much we weighed out. But we don't know the moles because we don't know the molar mass. That's kind of the goal here. So we already know that we have 0.446 grams of the acid, but what we don't know are the moles of the acid, the X there. That's what we're trying to find here. Now we know that at the equivalence point, the moles of the acid are equal to the moles of the base. And I know that I discussed just briefly right here the conjugate base. Make sure you know which base you're talking about here. So when you're talking about the equivalence point, it's the moles of whatever in your burette is equal to the moles of what's in your beaker. And this is for second semester general chemistry, so everything's 1-to-1 since we're not really working with polyprotic acids in terms of doing a big titration problem. If you're taking analytical, it's not always 1-to-1, but for us it is, like I said, in second semester general chemistry. So the moles of the weak acid in our beaker is equal to the moles of the potassium hydroxide in our burette. And so that's at the equivalence point. So that's what's going to help me figure out how many moles of the weak acid are in there, right? So that's the key component there. So I can figure that out from the equivalence point. And we estimated about 35 milliliters of the KOH was added to reach the equivalence point. We're going to convert that to liters because my molarity has volume units in liters. We were given that it was a 0.105 moles per liter KOH solution that was in our burette. And because it's a monoprotic acid, then it's safe to say that we have a 1-to-1 mole ratio between KOH and this unknown monoprotic acid. So we can cancel out milliliters, liters, and moles of KOH, and therefore we would get our answer in moles of the weak acid, which is 0.003675 moles of the weak acid, and now we can plug that in to solve for molar mass. So molar mass is equal to 0.446 grams per mole, 0.003675 moles, and therefore the molar mass of this unknown monoprotic acid is 121.36 grams per mole. Is your final answer there. So takeaway from this particular problem, make sure you do feel comfortable reading the graphs. If you were to get a question that had a graph in it to estimate where the equivalence point would be located, that would give you the volume that's in your burette, and that could help you figure out the moles of whatever is in your beaker. And also estimating about half the equivalence point because the pH is equal to the pKa at half the equivalence point. This is very useful to know. As well as, like I said, at the equivalence point, the moles of whatever is in your beaker is equal to the moles of whatever is in your burette. All right, if you have any questions, let me know.